Welcome to the Abstract Synthesis Podcast, where we go beyond the paper abstract to synthesize new ideas. Brought to you by AGI Research Lab and DIA. I am one of your co-hosts, Brian Landers, and this is my co-host.
Hi, my name is Mark Santolucido.
Awesome, Mark. I'm glad to finally get our podcast off the ground. First episode was with you, but now here you are, co-pilot with me for our first interview, which today is Kedar Namjoshi, who is a distinguished member of technical staff at Nokia Bell Labs. Which paper are we focusing on today, Mark?
This is a paper called Program Synthesis and Non-monotonic Reasoning. I had the privilege of getting to see Kedar present this at the Synth Workshop in Croatia just a few months ago. And he had a really wonderful presentation, so I'm excited to learn more about the backstory behind it.
Amazing. Welcome to the podcast, Kedar.
Thank you all. Thank you for inviting me. It's fun to be here.
Amazing. You are just exactly, your career is focused on what we like to focus on in this podcast. So really want to make you welcome and thank you for joining us today. Before we dive into the paper though, you work at Bell Labs. We are huge fans of Bell Labs at NDIA. Who's not a fan, I guess? I mean, it's just such a storied history, and I think it's been in existence for 100 years now. Is that right?
Yes, that's right. I think this year is the 100-year anniversary of Bell Labs. So
very exciting. Yeah. What team or department do you work at?
I work technically in the systems lab, or the systems side, the computer systems side of Bell Labs. But I guess I'm sort of more on the mathematical formal end of the systems department. So I also collaborate and work with people in the math department, the AI side of Bell Labs. So there's the networking folks. I mean, this is one of the really nice things about Bell Labs. It's a very collaborative place. And so people really go, make an effort to go across areas and try to find interesting things to work on.
That's very cool. I've been reading the book, The Idea Factory, and just kind of learning about, I guess it was sort of the, previous eras of Bell Labs before it was, Nokia entity. What is the research environment like there nowadays? Like, how do you select what to focus on in your work?
Yeah, that's a good question. So that's a really good book. I think that's definitely one of my favorites about Bell Labs. The research environment is maybe a little bit different from the one in the book. I mean, it's been a while since those things were done, but it's still the same in some important respects. So like I said, it's very collaborative, it's very open. You could just walk up to somebody and say, what are you working on? And then you get like maybe a half an hour lecture on whatever it is that they're doing. So people are really open about meeting and discussing ideas. And in terms of what you actually, like your question about how do you choose projects or how do you decide what to work on, it's really a combination of several things. It's kind of your own personal interests and expertise. Then there are questions that come from the business side of things. So, Nokia makes communications infrastructure. So, like pretty much, any phone call that you make in the US or actually in most parts of the world, there's a good chance that it goes over Nokia equipment. So the antennas, the fiber optics, the routing, processing, all of that. So the businesses, of course, have objectives, like, they want to have a fiber optic cable with higher capacity. That's an obvious objective. They want to switch packets faster, right? So these things come from the business side of things. And then there are also longer term sort of research directions, if you like. So AI or program verification or synthesis, those things would be kind of longer term topics.
Quantum's in there too, right?
Quantum is absolutely one of them. So so you sort of pick a project that tries to match all of these things or as many of these things as possible. And and so there is quite a bit of freedom given in terms of picking projects to work on.
It's amazing. Sounds like better than academia sometimes, Mark.
Yes.
I have a kind of a selfish question because we're setting up,
Yeah.
our systems at India. We're just getting started,
Yeah.
at the top of the year. Do you still all use lab notebooks at Bell Labs?
No.
No.
Unfortunately not. Although I still have my lab notebook, which I got when I joined Bell Labs, I don't know, 25 or so years ago. So, and I was afraid to write anything in it because it's this really nice, hardbound
I would be
lab
too.
notebook. And yeah, so I think I've only used up a few pages, but it's still sitting there. So yeah, unfortunately, we don't have. I think they don't even give them out anymore. So I'm
Got it.
hanging on to mine.
I figured it would mostly be digital these days anyway, but there was just something really cool about the hard
There
bound.
is something very cool about, yeah.
One more background question too. I know we met 7 or 8 years ago, actually, but it was only when we were preparing for this that I saw you actually worked with Dijkstra. Could you tell us more about that?
Well, that would probably take up all our time, but this is so I didn't actually work with Dijkstra, but when I was a grad student at UT Austin, he was a professor there, and I took his class. And then the more interesting thing was that he used to run a little discussion group called the Tuesday Afternoon Club. And we would meet every Tuesday afternoon. He would serve us coffee, things like that. And we would discuss papers, or just research. So I got invited to that. And that was a remarkable experience. So this was like a small group of people, maybe, I think all of us were in formal methods in some kind, or algorithms. And there were maybe 4 or 5 students, like PhD students, 2 or 3 faculty members, and then Dijkstra, who would sit at the head of the table. So, and this was a remarkable meeting in many ways, because partly what we would do is we would read other people's papers, sometimes our own, and one of the rules was that somebody had to read the paper out aloud.
The whole paper?
So,
wow.
The whole paper. Well, of course, yeah. So you'll see as we go that as I tell you more about it, that we didn't actually finish reading any of these papers. But so someone had to read the paper out aloud, including all the math. Then the role of the listeners was to object at any point that they didn't understand, or they didn't like the notation, or they didn't like the wording, or the grammar was wrong, or the punctuation was incorrect. And so there were, of course, lots of objections. So we typically didn't go, I don't remember going beyond like the first 3 or 4 pages of a paper. But the training you get as a result of that was just invaluable. That is one of the things I really enjoyed most about him and about his work. And so, yeah, I mean, of course, I respect his work tremendously, but just getting to know him personally was like a big highlight of being in grad school.
Very cool.
Do you have deep FOMO, Mark, for not being part of that?
Yeah, well,
it's pretty darn cool.
And so there's a bit of connection here to this paper, Program Synthesis and Non-monotonic Reasoning. I remember you were telling me that some of the inspiration for this came out of some work or some classes you took in grad school as well.
Yes, I think this work, so the paper that Mark just mentioned is the one that I gave at the workshop at CAV this year. But I also have an earlier paper. This is from Takas in 2022. And this is it's called Synthesis of Compact Coordination Programs, or something like that. Compact Strategies for Coordination Programs. And it really connects up, program synthesis with non-monotonic reasoning. And non-monotonic reasoning is this sort of area of logic which is about trying to formalize how people reason, like common sense reasoning. And what essentially it's very natural for us to keep revising our beliefs as we get more information. And this sort of revision is completely against how traditional classical logic does reasoning. So it's in traditional logic, as soon as you conclude something or you deduce a fact, that fact is frozen Like you can add more assumptions, you can add new information, but you cannot retract what you just concluded.
Right.
And people retract stuff all the time. So
Yep.
I took this. So I'd sort of known about non-monotonic reasoning, and maybe we'll get to that a little bit later too. But I'd sort of known about this for a while. I actually did an undergraduate project implementing a non-monotonic reasoning system, but I didn't really understand it well enough. And then in graduate school, I had this wonderful class by a really good teacher, Vladimir Lifshitz, and he kind of went into the theory and the logic behind this. And so the paper really talks about, if you think about a certain synthesis problem, then that turns the synthesis problem into one that's non-monotonic. And, we're trying to still figure out really what the connections are between the logic side of non-monotonic reasoning and how that affects synthesis. So I think that's still a very open research question.
You had this wonderful, just to make it like approachable for folks, but the non-monotonic example you had in the abstract was what is it? Like Tweety is a bird, all birds can fly. Tweety is a penguin, penguins cannot fly. And so now
Yes.
you have like invalidated the original constraint essentially. That's the idea here, right?
That's the idea here. That's sort of the classic example, and it's it perfectly explains how people are able to deal with this sort of change of belief. So at one point you believed that all birds could fly, and then later on you were told that, well, Tweety is a bird, so you just assume that Tweety can fly, and then you're told that Tweety is a penguin, but that doesn't invalidate anything, so you're good. But then you're told that penguins can't fly, and that penguins are birds. I guess you need that too.
Right.
So once you get to that point, you're in classical logic, you're in this big contradiction, right? And at that point, your head should explode, or you should just be able to derive or prove anything that you like. But what humans do is that they just say, oh, that's an exception to the rule. So they go back and kind of revise their belief and say, well, all birds other than penguins can fly.
Right. Ostriches. There's it keeps going too, by the way. Yeah.
Yeah. And various other things. So that's one way of dealing with this non-monotonic behavior. So there's this kind of logical system called default logic that says by default all birds can fly, but I can keep making exceptions to that rule. So the reason this connects to synthesis, and I don't know if you want to talk about that later or now, but
dive in.
Okay, is that in synthesis you're given a specification, and then you're asked to produce a program that meets the spec. And part of the difficulty with synthesis is just coming up with one solution to this problem. Like, even does there exist a solution? Like, if your specification is somehow internally contradictory, then there won't be one. But the other problem is that you might have too many choices. So you could produce for instance, if you're asked to produce a program that does sorting, it sorts a list of numbers, then there are many different algorithms that you could come up with. And so the question is, which one should you pick?
Is the explosion that happens over
it's
search.
an explosion of choices. Yeah, exactly. So you found one solution, but then you could have come up with 6 other solutions to that problem. And now which one do you pick? And the natural thing to do is to add some kind of preference mechanism and say, I'm going to prefer this kind of program, maybe one that's more efficient, to this other one. And as soon as you do that, and you say that I want the best program for my specification, then the synthesis problem becomes non-monotonic in a technical sense. And what that means is that you could have a program that's good for your current specification, but if you weaken that requirement a little bit, then the program that you have now may not be the best one for that specification. So you're forced to sort of revise your belief in that sense, in the fact that this is the best possible program. So that's the connection with I mean, that's sort of the non-monotonic property that comes in when you start asking for the best answer to your, to your synthesis problem. And I should say, I still don't know exactly where all of this goes, right? So this is more like an observation where, it might lead to something interesting, some interesting connections between non-monotonic reasoning as studied in logic and program synthesis. But I think those connections still need to be worked out.
So you were working on a very specific type of program synthesis. Could you give us some more context on what that means?
Yeah. So I can talk about that. And this was really how I got into synthesis in the first place. I'd sort of carefully avoided doing any synthesis research for a while because I knew the problem was extremely hard, right? And I'm trying to do, synthesis from logical specifications. But then a few years ago, I think it was like maybe 6-7 years ago, there was a lot of talk I was hearing about how everyone would have, internet-enabled devices in their homes. Everything would be IoT device controllable. You could just, tell it what to do and it would do it. That got me thinking about, well, who's going to write the control program that connects all these things together? So, I mean, imagine that you want to, you're driving up to your house and you want the garage door to just open automatically and the alarm system in your house to get turned off, right? As it recognizes your car and the fact that you're in it. Now, somebody has to write the program for this, or the program has to be created somehow. And so this is where I thought synthesis might play a role. That these were, in some sense, all control specifications. Like they were not really talking about, the actual mechanism of how your garage door opens. That's much more complicated. This was just saying, turn the garage door on or turn it off, or turn the alarm system on or turn it off. And the problem was, how do you sequence all of these actions?
This idea of, because you brought up the example of the garage door, and this seems like it led your thought process to this minimality. So like superfluous actions, right? The example you gave in the paper was, let's say it turns off, it has to happen within 2 minutes. You come to the garage, it opens, turns off the alarm system, but it also turns off the refrigerator. That's bad. Right. Your food's gonna go bad, Correct. And it's still actually, from a specification, it made a program that actually worked, but had undesired effects. So how did you kind of arrive at that observation? And then
I don't know. I think I think initially my initial work on synthesis in this direction was just trying to get the algorithms going, right? And there was some mismatch between what people had done before, which was they were trying to synthesize hardware circuits. And here I was trying to synthesize a control program. So I sort of worked with a summer intern, Suguman Bansal, who's now a professor at Georgia Tech, and one of my colleagues, Yaniv Sar, on this topic, just, getting the algorithms to work. And then once we got the algorithms to work, I started noticing that, sometimes the solutions had these undesirable actions in them. So these sort of superfluous actions that did not really contribute to meeting the specification, but could have very unexpected and possibly even dangerous side effects.
You mentioned, people are working on these algorithms and they were looking at it for hardware. I don't want you to undersell what you've done here. Yeah. Can you give us just a bit of context? What is this problem of synthesizing hardware? How long have people been looking at this? Where did it come from? And how long has it taken us to get here?
I can talk about that a little bit. So the hardware synthesis problem is maybe the original synthesis problem. So it goes back to Alonzo Church, who is one of the founders of computer science. And I guess sometime in the 1950s, I'm guessing, is when he wrote this paper saying that, well, wouldn't it be great if you could just say what the input-output behavior of a circuit was going to be, and then sort of hit a button and out comes the actual circuit that implements the specification. So his point was that, it's often much easier to describe what you want than to actually implement it. And circuits being a a good example of that. So he posed this problem, and I guess that led to a lot of follow-on work, really wonderful work that connected, these temporal specifications to file automata of various kinds, that connected those to, solving games of different types. So lots of beautiful theoretical work. And then in the around 1990, I think, Amir Pinelli and Ronnie Rosner, who is then a student, so they wrote this beautiful paper on how to take temporal logic specifications and synthesize circuits out of them. So a lot of the work up to that point had really been on, Church's original formulation, which was, I've got this input-output behavior that I'm describing to you, and could you create a circuit out of it? The thing that we wanted to do was we wanted to control devices. So devices don't have a common clock. They don't actually look like hardware. They send messages back and forth, and those messages or the interrupts from the devices can come at any point in time. So now you needed, a different way of formulating the problem in order to even solve it. And so that's really the initial piece of work that we did. And then that led to this observation that, well, we are getting these programs that, do what we want them to do, but they also do a lot of other stuff that we don't want them to do. And how do we constrain the synthesis method to, to make sure that they don't have all these undesirable actions?
What did you come up with in the paper? Did you go further to kind of propose any solutions?
Yeah. So I think what we came up with was basically this notion of trying to set up some kind of preference relationship between programs to begin with, but then also between the executions of programs. So, like, if you want this system to produce something where, it opens the garage door, then you can think of that as an execution where the signal comes in that your car is driving up, and then an action happens, which is to open the garage door. And that computation by itself is good, and it's better than the computation where the signal comes in and it turns on the sprinkler or the oven or whatever else you want to think about, and then opens the garage door. So you can say that one computation is better than the other. And then what we could do was to somehow take your original specification, which is, open the garage door whenever you drive up, and constrain it completely automatically to rule out all of these undesirable actions. Right? So you'd get a much tighter specification. So basically what we gave was a method that would take your specifications the way you wanted to describe them, and then automatically tighten them up so that the solution that you get would not have any of these undesirable effects. And then you could just send that tightened specification to any synthesis procedure, like, for instance, what we had to create this control program.
This makes sense.
And because of all the guarantees, the control program that you get would not have, would be one that did not have the undesirable behavior.
I have a question, actually, side question for Mark. This is making me recall our conversation about your grammar terminals, like, removing certain things and seeing if the synthesis still came up with the right solution, and then seeing, but sometimes you might cut something out that was required to find a solution. Is this different than what Kedar is talking about? Because there actually is like a real world outcome that is like almost binary that you can check against.
Oh, it's bringing up a really good question. So, Kedar, previously we had talked about some work on SciGuess, syntax guided synthesis, and one idea was to prune the grammar in order to prune your search space. And in a certain way, there's some similarities here, right? You're taking a specification and you're modifying that specification. Is there ever some risk that you might be modifying the specification in a way that makes it unrealizable or actually invalidates some claim?
It can certainly be unrealizable. That is true. But it's tightened in a way that, always respects the original requirement that you had. So, if you do get a program out of this tightened specification, then that program is guaranteed to meet the original requirements that you have. So the tightening is something that, people in non-monotonic reasoning in the logic side have thought about for a long time. So basically what you could do is you could just do all the tightening by hand. Like you could take your original specification, like, open the garage door, and then change it by hand to say, well, open the garage door, but, don't turn on the sprinkler and leave the oven on if it's already on. And, like all of these other things that you don't want it to touch, right? So you could do that by hand. But then this gets very tedious and to do to begin with. And it also can tighten too far, because the next specification or the next requirement that you come up with might actually require you to turn off the oven at some point, right?
Yeah.
And
Maybe
you're just
leaving the
constrained.
house and you want to make sure you turn
or
off
you're leaving the house and make sure the oven is turned off, right? But then all the tightening you did before is forbidding you to create a control program that does that. So in effect, every time you add a new requirement, you have to kind of recalculate what the correct tightening should be. You can't do it, separately per specification. And that recalculation is very hard to do by hand. And that's what we automated, essentially. So we sort of figured out a way of, you take all your requirements together and you figure out how to tighten them in such a way that the program that comes out won't have any undesirable effects.
Very cool. So one thing that you could think about is sort of this this incremental learning, in a sense, where you have some goals in mind and you set up your problem to synthesize a system with those goals, and then you learn a little bit more. Now you need to adjust your whole world model, and you learn a little bit more, and you keep adjusting as you gain more information about what your requirements are. I'll just make a pitch. This sounds, if you haven't seen already, ARC at Endia, where we work on something called ARC AGI, and there's ARC AGI 3 benchmark that was announced recently that focuses on solving games, as you mentioned previously. So it might be worth checking out some of the overlap here.
Okay. I'll take a look. Yes.
I guess, Kedar, jumping a bit ahead, but you some of your papers and your work have addressed things like, like in addition to like IoT, but robotics. So like multi-robot orchestration. What are kind of the challenges with, multi-agent systems with specifically program synthesis and verification?
The big challenge is that you really have to deal with all these multiple agents all together. And that, in the worst case. So because you can't really focus on, one robot and then ignore all the others, because the movements of that robot might conflict with what the other robots are doing. So in the worst case, you really have to treat them all together. And that leads to this big explosion in the state space, like in all the possibilities that you have to work with. And this is one of the, I think, the big open questions or the big challenges in synthesis is that, especially in these kinds of settings, in the multi-agent settings. So the device control part that we were just talking about with the garage door and so on, that's also a multi-agent setting. The robotics is a multi-agent setting. So there's lots of good use cases. It's just that when you get into them, when you have like 50 or 100 robots or 100 devices, then you get this exponential blow up in the worst case. And again, one of the papers that I had, we showed that this was in some sense unavoidable, that you're going to have to face it. But maybe the more practical question or the more open question is, do you really need to consider all 100 robots for your specification? Could you somehow, prune that group and say, well, this group of robots is all that I really need to look at for this specification? Or maybe you can sort of partition your specifications in a way that, deal with different groups of robots and, synthesize locally for each group and then combine the results together. So this sort of, divide and conquer strategy for synthesis, that's something that I think is still as far as I know, it's still very much an open question, is, what should be the right way of doing it?
There you go.
And in some sense, until you solve that, you're not going to get to real world problems, especially in these kinds of settings.
There you go for folks out there looking for ideas. Listen to Kedar here. That's a challenging one. It sounds hard, but it's in the LLM world, you've got all these multi-agent systems working together.
Right.
I'm sure there'd be a lot of cases where verification would be amazing. So super relevant. Anything else we missed before we talk about the kind of reception of the paper, about the abstract? Like, what big points should people come away with?
Yeah, I think maybe the biggest realization for me personally was that, program or logic, in particular temporal logic, but any kind of logic, is really good for specification because, you can say what you want and it's very permissive. Like it lets you implement that thing in many different ways. And for each different implementation, you still have the same specification. So the example of sorting is a very good one. So you just say, well, this is what it means to have a sorted array. And then you can have many different algorithms, all of which sort the array, but they have different trade-offs, right? So it's good for verification, but the permissiveness is not good for synthesis. And this is really where you start getting all these undesirable actions and, unoptimized code. All of that comes out as an example of something which you want to avoid during synthesis. So that's sort of the conundrum. Like you want to use logic to specify things because it's a nice, well-defined language. But then when you're doing synthesis, you have other factors that you have to take into account there.
Yeah, you've talked a lot about many dimensions of exponential blowup. So if we have lots of agents, they're all interacting, we need to somehow select a subset of them to focus on. And when we have many requirements, there's an exponential blowup here, and then never minding the exponential blowup in search, of course. So how do you see different strategies arising for this selection, this need for selection? Can we do this all purely symbolically through some sort of logical methods? Is there an opportunity for more AI-guided systems to be a part of this?
I think yes. I mean, there is an opportunity for AI guidance here, some combination of symbolic and AI methods. But like I said, this is still such an open question that I think people really need to think. I mean, this in some sense, this is one of the most important questions in synthesis, because it's the scaling question essentially. Is how big a problem or how big a specification can you actually synthesize a program for, and how do you make that task more efficient by maybe dividing up the problem into smaller sub-problems. But how you do the division, how you stitch the results together, I think these are all very open questions.
And if you had one paper or textbook that you would recommend, or lecture notes for people who wanted to take a crack at this problem?
I don't know if there is one, because at least not that I'm aware of, because it's a combination of ideas maybe from verification. So there are sort of ways of dividing up a verification problem into smaller problems. It's like modular verification is the keyword that you could look at. And perhaps those verification methods have something to say for the synthesis problem. But these connections really still have to be worked out. So there isn't any one thing that I could immediately think about and point to.
Definitely read all of Kedar's papers. That's an easy one. I think, what was the reaction? You presented this abstract at Synth 2025.
Yeah.
I know Mark liked it. He came back and said, we got to get this guy on the podcast. So that's one glowing review. But have you heard any other reactions from the community?
Well, it's maybe too early, but I think I got some really good questions at the synthesis workshop. I'm glad that I was there. And then I think I talked to people after that, so they were interested in the problem. And, some of them said they hadn't really seen it presented this way before. So I think all of this is encouraging. And part of my sort of reason for sending this work to the workshop was really to start a discussion. Like I know I think this is an interesting problem and an important one, but I don't have all the answers of how to solve it. So it was really to just, put the question out there and try to get people thinking on this topic. So we'll see, maybe in a couple of years, if you ask me, I'll have a better answer to, did this really have an impact? Did it get people to work on the problem?
Certainly inspired us. And I'm curious to see what you come up with too, between now and then. Thinking about the future, do you plan to kind of continue this work and keep pulling the thread? What are you working on now?
Yeah, so I'm sort of working on, those are two different questions, but the answer to the first one is yes, is that, this is a problem I'm interested in just intrinsically. So I do plan to keep working on it. I just need some good ideas, but I think, it's something that intrigues me a lot. And so I do plan to work. What I've been working on the last couple of years is actually a very different class of problems. So I think, as I mentioned before, I think I'm sort of interested in collaborative work, and that's one of the things that I enjoy about being at Bell Labs. And so one of the problems that I've been working on is really about blockchains and smart contracts. And this is a very different topic, but, so a lot of the smart contracts today get hacked and people steal, millions and sometimes billions of dollars, I think in total, from smart contracts nearly every year. So the question is, could you do something about it? Like, could you have... So one possibility is just to do verification of existing smart contracts, but those contract languages are often very complicated to verify. So one of the things I've been exploring is, could you sort of have a nice combination of, a good language design coupled with verification? So could you sort of design a language that makes it easy to verify the security of smart contracts? Basically the fact that they cannot be hacked into. That's what you want to show. So I've been working on that. So there's a paper out earlier this year on the design for this language and the corresponding verification system. So that's one thing. A second completely different topic is on how to update large networks and network configurations. This turns out to be a really tricky problem because you have a network that's conveying traffic and you want to now reconfigure it. But you have to do that on the fly. You can't, shut down the network for a few hours because it would make a lot of people very unhappy. So you have to sort of change the configuration, one router at a time.
Wow.
Okay. But now the problem is that, some of these routers are running the new configuration and some of them are running the old. And so you could have tremendous confusion in how packets get routed. So
compatibility, like backwards compatibility for them in flight or whatever. That sounds hard.
Exactly. So you have like a classic, version conflict type problem, which also happens in software, but, this is in particular for networking. So essentially what I did last year was to come up with some networking folks, was to come up with a new algorithm for reconfiguring networks that avoids this conflict from happening at all. So it sort of, it kind of gradually changes the configuration over while making sure that packets don't get into some kind of confusing situation because they have gone through, old as well as new configurations. And that was published at SIGCOMM, which is the main networking research conference. So if people are interested, they can look that up. So this is sort of, what I enjoy about being at Bell Labs, as you can sort of tell from these very different topics, is that you get to work on all sorts of interesting questions. And, often these are prompted by like hallway or, coffee machine discussions with people. And they turn into research questions and then interesting papers.
I love that. That's really cool. I love how grounded your work is too in these things like IoT and It's funny, when I was an investor investing in tech startups, there were some startups that did, verification of like smart contracts between devices. So, filling up gas, like one device or whatever, they could have a smart contract that said, okay, the gas has been refilled or whatever. And you're right. Didn't think of it that way, but it's a verification problem. It's a synthesis thing. So that's pretty exciting stuff. So Kedar, looking across your work from this, verification, some of your papers were about, secure compilation, synthesis.
Yeah.
What do you think, from your view, what is the next big frontier for formal methods and, with AI blowing up and,
Yeah. So I don't know if I can really speculate, but I think there's one. So it's sort of coming back to synthesis. I think that is one of the big dreams that people have had for a long time, and where you could just say what you want and then programs get written for you automatically, right?
That's the dream.
So it is a dream. It's been a dream for a long time, but maybe now with AI and other techniques, and just the fact that our techniques have gotten better, our understanding has gotten better, that maybe it's a good time to start going really hard for that that goal. So, and like we've been discussing, there are lots of challenges, and you have to solve them one at a time. But I think it's sort of both from the practical point of view, like, it would be wonderful if you could just say what you want and programs get written for you. But also just intellectually, I think as scientifically, it's a really interesting and challenging problem to work on. So it's sort of, I think it interests people from both sides. And I think that's, so that's maybe one of the things that I would expect to see much more of in the next few years.
Yeah, we're certainly inspired by that. Any last thoughts from you, Mark?
Yeah, I think, one of the things that we are seeing is, just to a certain extent, you can say what you want and get the code with code models and LLMs and all of this stuff. But the big gap remains that, once the reasoning gets hard, once you have these sequences of actions, once you say, I don't want you to do extra stuff, we've all been there.
Right.
We have some good code, ask the LLM to modify it, and now it's doing all kinds of other stuff we didn't ask for.
Yes.
Tackling these issues is still very much an open problem.
This is very cool. All right. Well, I know you gave a talk earlier as well. Synth was kind of connected to Cav, right? And on YouTube is one of your talks from there. So I'll definitely link that in the show notes. Anything else, you recommend people check out?
No, I think these would be good starting points. But there's a lot of other ways of doing synthesis. If people are interested, Mark, for instance, has been working on different methods for synthesis. There's a lot of different ways of tackling this problem, and I think people should look at all of that.
Excellent. Super inspiring. Kedar, you are just the perfect guest for what we're focused on here. So thank you for your time and your brilliant insights. We look forward to seeing more of your work, and hopefully at some point seeing a published version of this abstract and plenty of other stuff to check out. But really, thank you so much for your time.
Thank you. I've really enjoyed this, and thanks for inviting me here.
By the way, was this your first podcast, Kedar?
It was my first podcast.
Amazing. Total pro. Would never have guessed that.
Thank you.
Bravo.
Thank you. Yeah.
Cheers, Kedar. Thank you so much.
All right. Okay.
Thanks
so much.
Bye.
Yeah. Bye.